Exercise 1610 says for each of the following compounds, identify the expected chemical shift for each type of proton. And by proton, they just mean each hydrogen. There's one proton in the nucleus of each hydrogen. So first, so hydrogen and proton are often used synonymously. So first, let's draw all the hydrogens in. Let's look at and see how many hydrogens there are, what types of hydrogens there are in this molecule. So these are all of the hydrogens in red. And we'll want to go through a similar procedure as we went through for the previous problem, 16.7. We want to find general areas where we're likely to find certain features. Once we have those down for each hydrogen in a unique electronic environment, we will change it based on electronegative atoms nearby. So the first, there isn't a lot of symmetry in this molecule. So we'll notice that that hydrogen there is in a unique chemical environment. It has nothing to the left of it and the whole molecule to the right of it, and so it will have its own peak in the NMR spectrum. And if we look at the type of hydrogen that it is, you'll notice that it is an aldehyde hydrogen. So we would expect that to appear at around 10 parts per million on an NMR spectrum. All right, next. We have these two hydrogens here. And for both of them, there's the aldehyde to the left, the whole molecule to the right. So they're equivalent. Those two hydrogens are in the same electronic environment. It's different from the previous hydrogen that we looked at, though, so it'll have its own peak on the NMR spectrum. Now, at first glance, you might be tempted to say it's a CH2. There's two hydrogens coming off of a carbon, but you have to be careful anytime there is a double bond in a molecule, because these are not just any CH2s. Both of these hydrogens are allylic. They're both one atom away from an atom in a double bond. That makes them allylic. And the allylic hydrogens won't show up at 1.2. They'll show up at around 2. So because of that double bond there, that CH2 that we're looking at is allylic, and the absorption for it will show up at around 2 parts per million. Next, we run into a hydrogen attached to a double bond. Certainly the first time we run into that in this molecule. And so it's in a unique electronic environment. You have the weird thing to the left, weird thing to the right. No other hydrogen in the molecule is surrounded by those same groups, and so a unique amount of electron density will be around that hydrogen, and it'll take a unique amount of radio waves, energy in radio waves, to flip the nucleus. So what type of hydrogen is it? Where would we expect that to cast a shadow? Well, that's a hydrogen on a double bond. In other words, that's a vinylic hydrogen. And vinylic hydrogens appear between 4.5 and 6.5 in an NMR spectrum. If we look at the next hydrogen, it's also vinylic, but it's in a different environment than the other one. This one's further away from the aldehyde and closer to the alkyne. So it's a different electronic environment, so it'll be a separate peak, but it is also on a double bond, on a carbon in a double bond, and so it is vinylic. So we would expect this one to appear between 4.5 and 6.5 usually. All right, next we have hydrogens here, these two hydrogens. They're in a unique electronic environment. We've got the double bond to the left, the triple bond to the right. It's different from anything we've seen so far, so those hydrogens will have a unique amount of electron density around them, and so it'll take a unique amount of radio wave energy to flip the nuclei in the external magnetic field, or I should say in the net magnetic field. Because those hydrogens are CH2, you might be tempted at first to think that the peak would appear at around 1.2, but don't forget the double bond. When you have a double bond, you have to be especially careful because those hydrogens can be allylic. The hydrogens are one atom away from an atom in a double bond. That makes them allylic, and that means that they feel that magnetic anisotropy like we discussed in a previous video. and so the absorption for them is shifted up a little bit. You'd think it would be around 2. All right, so next, these hydrogens here, they are really close to an alkyne. They have the whole weird molecule on the left. This is a new electronic environment for hydrogens in this molecule, so these will be represented by a new peak. And those hydrogens are not allylic. They're 2 atoms away from an atom in a double bond. And so they're really just a CH2. So these you'd expect to appear around 1.2. Finally, we have a hydrogen on an sp3 hybridized carbon. We have this hydrogen here. And that hydrogen, a hydrogen on an sp3 hybridized carbon, is going to be shifted, and it should appear around 2.5 parts per million. So those are the numbers. Those are the number of peaks and the chemical shifts you'd expect for them on average. We just have to be a little bit careful, because if we have any electronegative atoms, those will change the chemical shifts a little bit. And so in this case, we do have an electronegative atom. It is the carbonyl right there. And so that's the carbonyl carbon. Right next to it, that's the alpha position. And if you're alpha to a carbonyl, you have to add 1 to the shift. And so these brown hydrogens really would appear not at 2, but at 3. Also, the green hydrogen is beta, right? Here's the carbonyl, alpha to it, beta. And if you're beta to a carbonyl, then you add 0.2. So 0.2. In other words, oops, sorry, that should go with the green one. So you add 0.2, and so you'd expect that to be between 4.7 and 6.7. Oops. So since that is the only electronegative atom in the molecule, and we've considered all the alpha or beta hydrogens next to it, these would be the predicted chemical shifts. Now, if you're wondering, wait a second, how about this hydrogen here? Note that that is not alpha or beta to the carbonyl. That is on the carbonyl carbon. And so the shift that's related to its proximity to the oxygen and to the carbonyl is taken into account already when we saw the shift for that structure. And so these are the shifts you would expect for these different peaks. We'd have a peak at around 10. As we saw, we'd have a peak around 3, a peak around 4.7 to 6.7, 4.5 to 6.5, 2, 1.2, and 2.5. Oops. So those are the expected chemical shifts for each type of proton or hydrogen in this molecule. Now for the next molecule, we're going to go through the same procedure. First step is just to recognize what types of hydrogens are in this molecule. So let me draw those in. Okay, let's go through these one by one. We have hydrogens here on the left. Now they have nothing to the left of them. The whole molecule to the right, this is a unique electronic environment. They'll show up in one peak. It's a CH3, so you might be expecting this methyl, but anytime you have that double bond, always be careful. These hydrogens are 1 atom away from an atom in a double bond. That makes them allylic. So for these hydrogens, you'd expect a peak at around 2. The hydrogens on the double bond, those actually are separate. Because the double bond cannot rotate, Each of these hydrogens are in different electronic environments. The brown one is, for example, cis to this side of the molecule, whereas the green one is cis to the opposite side of the molecule. So because the double bonds can't rotate, those are going to be two separate signals. Both of those hydrogens, though, are vinylic. They are on an atom in the double bond. And so you'd expect the peak to be around 4.5 to 6.5 for both of them, but they would be separate peaks in that range. Next, we've got a couple hydrogens here. Those are in a unique electronic environment. They've got that double bond right to the left, the alcohol close to the right. Those hydrogens, you might be at first tempted to say that they're methylene, CH2. But anytime you have that double bond, be careful. These hydrogens are one atom away from an atom in a double bond. That makes them allylic. So they'll appear around 2. Next, we have these hydrogens. Those hydrogens are in a new electronic environment. They're further away from the double bond and much closer to the alcohol. So it's a unique electronic environment that will be represented by a separate peak. And because these hydrogens are not 1 but 2 atoms away from the atom in the double bond, they are not allylic, they are just methylene, CH2. So you'd expect them to have an absorption around 1.2. Finally, the hydrogen on the oxygen is different. No other hydrogen in the molecule is like that. And so that will be represented by a unique peak as well. A hydrogen on an oxygen, we've seen, appears between 2 and 5. So we'd be looking for a peak somewhere in that range. So in the NMR spectrum for this molecule, you would have 6 different peaks. Now these are the average ranges where they'd appear, but we do have to take into account electronegative atoms and how those electronegative atoms shift the averages that we just wrote down. The one electronegative atom we have here is this oxygen. The purple, these light purple hydrogens, are alpha to that alcohol. If you are alpha to an alcohol, that adds 2.5 to the chemical shift. So really you would expect to see the peak for those hydrogens at 3.7. Then the blue hydrogens, those are alpha beta. So they're beta to the alcohol. And if you're beta to an alcohol, you add 0.5. So we'd add 0.5 to that, and you'd expect to get the signal for that at around 2.5. So we have these different signals. We now know the number of signals, different signals we have, and we know about where they would appear. And so that helps to act as a sort of barcode for this molecule. Having this many signals at these positions would allow you to determine the structure that gives rise to those signals. And it answers the question, the expected chemical shift for each type of hydrogen. So for C, we're going to follow the same procedure. First step, we'll draw all the hydrogens in. Okay. So there's no symmetry in this molecule, so we'll go one by one through each group of hydrogens. These hydrogens right here are in a unique electronic environment. They have the whole molecule to the left, nothing to the right. And so you might think at first that it's a methyl, that they're methyl hydrogens, so they'd appear around 0.9. But any time that you have a double bond, always be careful. Watch out for allylic positions. Those hydrogens are one atom away from an atom in a double bond, and that makes them allylic. So the signal you'd expect for them would be around 2 rather than 0.9. Next, we have this hydrogen right here. It's, of course, in a different position. It's much closer to the double bond, has nothing on the other side. So that'll be a second peak. That hydrogen is attached to an atom in the double bond, and that makes it vinylic. So the signal you'd be looking for there would appear between 4.5 and 6.5. Then we have hydrogens down here. So those are in a unique electronic environment. They're right next to the double bond on one side, they're not on the other. And so that'll be a third peak on our NMR spectrum. You might at first blush be tempted to say that, well, those are a CH2, probably methylene. But anytime you have a double bond, be very careful. Because those hydrogens are one atom away, the carbon that they're on is one atom away from an atom in a double bond, they are allylic. And so the signal you would expect from them would appear at around 2. Then, next group of hydrogens. These hydrogens are in a new, unique electronic environment. They're 2 carbons away from a double bond on one side. They are 3 carbons away from the double bond on the other side. So, new electronic environment, that means they'll absorb a unique amount of energy that will be represented by a new peak in the NMR spectrum. And these are indeed methylene. These are CH2. They're not allylic because they're 1, 2, 3 atoms away from an atom in the double bond. So those are methylene, and you'd expect the peak for them to appear at around 1.2. These 2 hydrogens share a unique electronic environment. The pieces that are on either side of them is different from the pieces of the molecule that are on either side of any of the other hydrogens. So they'll be represented by a unique peak because they're in a unique electronic environment. And those are also methylene hydrogens. You'd expect them to show up in a peak at around 1.2. Notice they're not allylic because they are 1, 2, 3 atoms away from an atom in a double bond. To be allylic, you have to be 1 atom away from an atom in a double bond. Then we have these hydrogens here. And those hydrogens, you might at first blush be tempted to say are CH2 methylene hydrogens, but they're 1 atom away from an atom in a double bond. That makes them allylic. And so the signal for them should be around 2. Now, those are the average signal shifts, the chemical shifts for those. But we do have to consider if any of those shifts are changed by electronegative atoms nearby. But we do not have an alcohol, an ether, an ester, or a carbonyl anywhere in the molecule, so these shifts don't change. And those are the places where you'd expect to have these 1, 2, 3, 4, 5, 6 peaks in the NMR spectrum. Finally, for D, the procedure is going to be the same. So we're going to first draw in all the hydrogens. There isn't too much symmetry in the molecule. You could argue that there's symmetry, there's like a slice of symmetry going straight up and down in the plane of the page. Let's go one hydrogen at a time, either way. These three hydrogens here, that group of hydrogens, is in a unique electronic environment. Nothing to the left, the whole molecule to the right for all three of them, so they'll show up as one peak. Now that's CH3. It's not close to any double bonds, so it's just a run-of-the-mill CH3, and that's a methyl group. So you'd expect that to appear around 0.9, the peak for those hydrogens. And for the next hydrogens, you'll notice these hydrogens here are actually in the same electronic environment as the other methyl group hydrogens there. And you can always tell, because if you ever count the distance away from different things in the molecule, they'll be the same. So for the hydrogen, the methyl group on the left, that's 1, 2, 3 carbons away from an ether. They are 1, 2, 3 carbons away from the triple bond. For the carbon on the right is 1, 2, 3 carbons away from the, or 3 atoms away from the ether. And those hydrogens are 1, 2, 3 atoms away from the triple bond. In other words, they have the same groups, the same distance away. That's just another way of saying that these brown hydrogens are all in the same electronic environment. So those are all CH3s, and there's no double bond nearby, so they couldn't be allylic, so they're just going to be methyl groups, and you would expect for them to appear somewhere around 0.9 parts per million. Finally, we have our hydrogen on an alkyne, or alkynyl hydrogen, and that would appear at around 2.5. So if you put this molecule in a spectrometer, turn on the magnet, shine the radio waves through, you'd expect to get around 3 peaks in the spectrum, 3 shadows cast, when these nuclei in 3 different electronic environments flip from the parallel to the anti-parallel position relative to the external magnetic field. And these are the average places where you'd expect to see the signals, but we have to take into account where the signals would go when they're exposed to electronegative atoms nearby. So, for example, these yellow hydrogens are alpha to this ether. That oxygen is an ether, it has a carbon on both sides. And right next door to it, 1 atom away, is a position, and that's the alpha position. So if you're alpha to an ether, then you have to add 2.5 to the chemical shift. So 0.9 plus 2.5, that's 3.4. So ultimately you would expect to see a peak for those hydrogens at 3.4 parts per million in the NMR spectrum. Okay, how about the brown hydrogens? Well, those are beta. Right, here's our ether. Those are beta to the ether. There's the alpha position, and the next position away is the beta position. All of those hydrogens are on the beta position. If you are beta to an ether, so here's an ether, if you're beta, you add 0.5. So you'd get another shift there. You'd add 0.5 to that, and ultimately you would expect to see the peak for those hydrogens at 1.4. Finally, the green hydrogen is so far away from the oxygen, the electronegative element, that the pull of the oxygen's electronegativity doesn't affect this shift significantly, and so you'd expect to see that exactly where it is, around 2.5. So this was just more practice with using standard chemical shifts and the effects of nearby electronegative atoms to predict where the shadows cast by the hydrogen in different electronic environments would appear on an NMR spectrum.